morning, ladies and gentlemen. I want to give a presentation about the surface temperature retrieval from multi-source remote sensing data. This is my colleague Li Qinhuo is my PhD student and my colleagues. I'm from State Laboratory of Remote Sensing Science, Institute of Remote Sensing and Digital Earth, Chinese Academy of Sciences. So our institute, the full name is the Institute of Remote Sensing Applications. So our institute has just been merged with the Center for Earth Observation and Digital Earth. So the new name for the institute is Remote Sensing and Digital Earth. The outline for the decision including 4 parts. The first part is detection. So as we know, the land surface temperature is about the most important key parameter in the land surface and atmosphere interactions. We have a lot of applications such as global warming and drought monitoring, and we also use the land surface temperature to calculate the long wave radiance from the land surface. So we can use to calculate the land surface energy balance. So we can anyway, land surface temperature has a lot of applications. So up to now, the thermal-infrared remote sensing is a unique way to obtain land surface temperature on regional or global scale with different spatial and temporal resolution. So this is why the thermal-infrared remote sensing is also very important for land surface temperature. Up to now, there are a lot of thermal-infrared sensors. You can see from the table. The AHI is a long-time series sensor, including 2 thermal-infrared parameters. So as the AHI have 2 thermal-infrared parameters, so we can use the frequency of the them to retrieve the surface temperature, and then we use the frequency of them for the land surface temperature retrieval. And then we can also have the multi-local thermal-infrared sensors such as the ASTA. We have more than several TR band. We have 5 TR band for the ASTA sensor, so we can use the land surface temperature retrieval of them with a multi-channel of them. And the MODIS is also a very important sensor, including several thermal-infrared bands. So we know the MODIS have totally 63 bands with different spatial resolution. And for the thermal-infrared band, the resolution is 1 kilometer by 1 kilometer. And the Landsat TM, ETM, and is also very important thermal-infrared camera. So including only one channel TR band. It means we have to use the one channel of the sound to choose the land surface temperature. And the HSR and the AHSR is also a very important thermal-infrared camera. Because these sensors have 2 via angle for the land surface temperature observation, it means we can use the multi-angle observation to retrieve the component of the land surface temperature. It means we can retrieve for example, retrieve the vegetation temperature and the vegetation and the soil, the subground soil temperature. So this is why the HSI and the AHSI are very important for multi-angular thermal-infrared remote sensing. And the various is the visible infrared image radiometer should onboard the NPP, which was just launched in 2011. So I think this sensor is the next generation of the MODIS. I don't know, the MODIS is running now, but after the MODIS, maybe we can use the various. That's why the NPP, and the next generation is the JPSS. So we have also several sensors in China. So you can see from the phone 1 and phone 3, and the phone 2 and phone 3. And we have also on the Ceres 1 and Ceres 2, we have thermal-infrared camera. And today I will talk about the river and the merits onboarding the phone 3, A and B. The phone 3A was launched on 2008 and 2002. Phone 3B was launched on 2010. This summary is similar with the HSR, and the merits is similar with the MODIS. So we have also several kinds of thermal-infrared values, visible and near-infrared values. And of course, we have another sensor on board the STO1, which means the environmental monitoring satellite transportation. So here we also have one camera. You will see here 700 camera have 300 meter spatial resolution. Because today I want to introduce the density temperature of the gems for the formula 3 and A and B. They were launched on May 2008 and November 2010. So for the various have 10 channels with 1.1 kilometer spatial resolution, and this was in 2014. So this is similar with the NOI RR, yes. And the memories have 20 channels, so 10 visible band with spatial resolution of 250 and 1,000 meters. And it has 7 near infrared channels with 250 and 1,002 meters, and 2 short infrared channels with 1,000 meter resolution, and 1 simple infrared channel with 250 meter resolution. So you see, we can have the two kind of spatial resolutions for a lens spectral temperature product. One is from the Willis is 1.1 kilometer, and another one is simple camera on for the various is 250. Today I just want to talk about the various lens spectral temperature which will all present. So we can see we can use various to retrieve the lens temperature for the global. So this is an example of the lens temperature for retrievals from the previous global on 2009, and this is the global sea surface temperature retrieval from the formula 3. Objective of this paper is just want to improve the practical algorithms for lens temperature retrieval from formula 3 various and various sensor data. Another objective of this research is to evaluate the consistency of the various lens temperature with different sensors such as the MODIS and the various together. So the second part I want to introduce the multi-channel algorithm to retrieve the lens temperature. So you see for the semi-infrared parameters, the quantitative measured radiance by the satellite can express as the equation. So this is the radiance observed at the satellite. So it's including the radiance from the land surface transmitted by the atmosphere. So it means times the transmitted to the atmosphere. And plus the second term is the radiance down that is upvoting the atmosphere radiance. And another one is the scattering effect of the atmosphere. So as you can see, for this term, it means the radiance from the land surface is including several parts. The first part is the land surface emitted terms is plasma temperature. You can use the plasma function to calculate the plasma temperature and times the emissivity of the surface. And then the second term is this one. It means reflected the atmosphere downward radiance. And another one is the land surface reflected solar radiations for the several infrared parameters. This slide just to explain the different terms meaning of this formula. How to retrieve the lens temperature from the satellite observed radiance? Up to now, generally we can have 3 kinds of algorithms. One is for the single channel algorithms, and another one is frequent algorithms, and another one is multi-channel algorithms. Maybe frequent algorithm is the most important one for the lens temperature retrieval, especially for the global lens temperature retrieval, because they have been widely used for the LHR and the MODIS and the AHSR, also used for the formula 3. So what is the single channel lens temperature? Basically, we have different single channel lens temperature algorithms. One is the radiation transfer equation method proposed by Soprano. These algorithms wanted the atmosphere profile and the lens surface emissivity. And another Qinhuo from 2001. These algorithms need the atmosphere transmission and the effective temperature and the lens emissivity. And the single channel algorithms, another research was proposed in 2003 and 2009. These algorithms need the near surface temperature and the moisture of the atmosphere, and also need the lens emissivity. For the China HQ1 satellite, we have also developed some the single channel lens temperature retrieval on the similar algorithms. And for the split window algorithms, they are widely used for the AVHR remote sensor. So we have a lot of split window algorithms. As we know, the split window algorithms were successfully used for the for the sea-surface temperature retrieval. So they have been operationally used. But for the land surface temperature, up to now, the split window algorithms face several challenge issues because the land surface temperature accuracy is not so good up to now. From these different equations, maybe from different algorithms for land surface temperature retrieval, you can find out the land surface emissivity is a very important parameter in the algorithm. Another one is the atmosphere profile. It is not needed for the atmosphere profile, but the algorithms need some kind of atmosphere parameter. For example, the atmosphere total water vapor content atmosphere. So anyway, we have different kinds of algorithms. And the multi-channel lens temperature algorithms is so you can see currently there are three kinds of algorithms: one temperature independent, spatial index, TISI, and so. These algorithms can be used. We can use the daytime and nighttime observation for the semi-infrared band and the middle infrared band to retrieve the lens surface temperature and lens surface emissivity together. So, and another one is multi-band algorithm used multi-state and night times. So these also can use algorithms to the emissivity and the lens surface temperature. Another kind of algorithm is for the sensor such as aspect, because we have several different bands. So we can use the lens surface temperature emissivity separation algorithms, TES algorithms, to retrieve the lens surface temperature and the emissivity. However, for the only three various and Navier sensor, you can see we have different kind of band here. So because the lens surface temperature retrieval, we need the split window channel. So we can use the various 4 and 5 to use for the split window algorithms. And we need the lens surface emissivity. How to get the lens surface emissivity? So we just want to use the channel 1, channel 2, the visible and near infrared band. You can use YouTube to calculate the station index, and then we can based on the station index to calculate the lens surface emissivity. And then we can use the various band 16, 17, and 18. These band is based on the water vapor content. So we can use this band to retrieve the atmosphere water vapor content, and then we can get the atmosphere information to support the VRR lens surface temperature retrieval algorithms. So this is just to show some of the equations processes. So without the configuration reflecting effectively TIR band, then the radiation transfer equation can be simplified as the radius observed by the satellite is equal to the tau, which is the transmitted of atmosphere, and the emissivity, and the lens surface temperature, plus the reflected down was the atmosphere radius, and plus the atmosphere upward radius. Let's assume the atmosphere downward and upward radius is equal to this one and this one. It just means we can use the effective atmosphere temperature for the upward and downward atmosphere radius calculation. Why we do that? Because it's very difficult to get the atmosphere profile of the lens surface temperature. But we can try to get the equivalent atmosphere the temperature. So we can use the profile with several parameters, but equivalent temperature, air temperature, the temperature is only one temperature. Then we can get the Gini equations. So we can select the optimal path angle of the upward transmission corresponding to the downward radius in the thermal channel. Why we do that? Because the upward effective temperature and upward and downward atmospheric effective temperature is different. So we have to connect the these two parameters together, then we can reduce the unknown parameter in the equation. So then we can get the Gini equation. We can derive the equation as optimal radiation transfer equation with separate TS to different sub-temperature range J for Planck function. It means in the window of the we always use the